Hello and welcome to Toddcast number 17. So we're continuing on with acid and bases. So far the Toddcast we've dealt with, we first dealt with just the basics and definitions of what an acid and base were. Last one we dealt with mathematics and then predicting an K-equilibrium for an acid-base reaction. And this time we're now going to get purely conceptual and try to learn the nuances between determining which acid is stronger and which acid is weaker, and subsequently which base is stronger and which base is weaker. So lots going to go on this time. Now we're going to actually do a lot more conceptual. So hang on. The answer to every question you'll ever have in OChem, except for maybe three, is resonance. It explains everything. Sharing electrons through a pi network is incredibly common in the molecules we deal with in organic chemistry. There'll be some exceptions. We'll deal with size in some instances, bulkiness of a compound known as steric hindrance, inductive effect based on electronegativity, but by and large, resonance is going to be massive. So in a previous podcast, I told you this pK is 10. Now I'm going to be a little more specific and say it is 9.95. Okay, we also looked at another compound that was just like phenol. The only difference is it has, this is carbon 1, 2, 3, 4. At the fourth position, it has an OCH3. Keep in mind they're lone pairs on the O. And there they are. Okay, those lone pairs make it an electron donating group. So we mentioned that with resonance. So now I'm going to see what the exact effect it's going to have on pKa. So generally speaking, lone pairs equal an electron donating group. So that means it's going to donate in. So this lone pair is going to go in. That creates 5 bonds to that carbon, so that has to move over here. This is going to ultimately move to there. So the structure I've just created. Here's the benzene ring. Here's the OH coming off. Here's my lone pair. Here's my OCH3. The remaining lone pair and the positive charge on. Because negative is real close to the OH, that's going to make it less acidic. A negative charge there will make it less likely to give off an H plus and have two negatives really close to one another. Can't facilitate that. It can't stabilize a negative charge on O by putting a negative charge near it, which means you made the acid worse. Weaker acids have a higher pKa. So pKa is going to be greater than 9.95. Hopefully that resonance seems reasonable. So the exact number is 10.24. In a previous one, I gave it as 10.8, I believe. So once again, want to point out numbers for pKs will fluctuate from text to text, moment to moment, book to book, lecture to lecture. So knowing it relatively well is better than knowing absolute numbers in any given lecture. So I both apologize for having fluctuating numbers, but also want to point out I present that on purpose so that you don't lock into any specific number. You know roughly what they're at. So phenols are 10-ish. When you have a donating group, they're going to be higher than 10. So if you have a withdrawing group, it's going to be lower than 10. That is what I want you to know. Be able to conceptualize and rationalize why one is stronger or weaker than the other is far more important than memorizing numbers. Okay, so another compound. This time, it has a pi bond. The first atom attached has a pi bond. Pi bonds equal electron withdrawing group because pi bonds can pull away. So let me get rid of that for now and let the computer kick in and tell me the pi bond equals electron withdrawing group. So if this pulls away, and I've been lazy and I've not drawn my lone pairs on that O, that breaks this pi bond, so this is short. So this pi bond can come down here. This pi bond can come down here, and lo and behold, there are OHs, a lone pair on an OH that can come down. So because it is stealing away the electrons, I make an electron poor or more positive. More positive is going to repel an H plus away. It's going to stabilize at O negative. So if this H is lost, so let me draw it as a lost H for the time being. That new lone pair that forms here, the negative charge, will want to go in. So resonance withdrawing group will stabilize the anion of the conjugate base. If you have a more stable conjugate base, the more stable the product, the more reactive or unstable the reactant. So if I have a more stable conjugate base, it must be a stronger acid. A stronger acid would have a pK less than the reference. Okay, so I'm going to get rid of what I drew there and put the OH back in. Ends up that one's 8.05. And we had it last time, I had at 8.4. So close, but again, I don't have it consistent from one lecture to the next. So there's no reason for you to have it consistent. And truth be told, I obviously could make it consistent from one lecture to another. So again, I want to point out, this is on purpose so that you don't try to memorize numbers. Finally, this one, but with a little bit of a change, this O can donate in. So any donation from up here to push the electron density here. So let me recolor this. Let me do this one in green. So this green donation will push it here. This yellow donation will push it there. So this one had just the equivalent. The red here equals the yellow here. So it will withdraw it away. This one, because of slight donation here, means this pathway, this donation, is going to be less substantial. So it's not going to be able to stabilize that O as much, at O minus. So it's going to make it less. It is pulling it away, so it's going to make it less, but not to the same magnitude as this. So it's going to basically be less than 9.95, but greater than 8.05. So less than this, but greater than this. So about 8.47. Okay, so this is the impact of resonance. You will have to identify which acid is more acidic, which is less acidic. You do not have to memorize numbers, but donating groups you have to know will make it less acidic. Withdrawing groups will make it more acidic. Ketones were better withdrawing groups than esters. Ooh, it's ester, there's two O's. Ketone, R group with a double bond O and an R group. Okay, so the next on the thing on the agenda, so resonance is the most important. So I'm going to hang on to that thought. Resonance wins. Inductive effect is going to be when there isn't resonance in those rare cases, I should look at inductive effect. If you know anything in physics, I'm going to use a physics example to get us started. If I have two spheres, if I make one sphere positively charged, let's say with a +6, if these spheres are close enough, then negative charges on the sphere, electrons, will go this way, leaving behind a positive. So this positive sphere here is inducing a dipole. It's inducing a delta minus delta plus. So this is what's known as an induced dipole generated by charge asymmetrically surrounding that sphere. Okay, so I want you to contemplate what you think will happen if we were to add double the charges. So if the magnitude of this was +12 instead of +6, would that have any bearing on it? And hopefully your instinct tells you, yeah, the bigger the plus charge, the more it's going to create charge inequity, charge distribution. So the bigger it pulls, the more it pulls, the bigger the charge, the more this is going to be shifted over. Okay, that's going to be one concept. So the more it pulls, the greater the impact. And then proximity. The closer they get, you feel it more and more and more. So the force is going to be greater. The further away you get, the less. So if I move this sphere with +12 further away, I would go back down. I'd start losing some of the negatives here and positives there. If I move it closer, I'd start seeing it amplified. So induction and induced dipole depends on strength of charge and proximity. Okay? Induction and inductive effect are the exact same concept, except we're not doing physics in charged spheres. We instead are doing molecules. Okay, so when you're dealing with molecules, atoms within them will share bonds unequally. You have to remember Fonkelbrish. So Fonkelbrish, F-O-N-C-L-B-R-I-S-C and H, the common elements found in an organic chemistry class. So for instance, here's my benzoic acid. pK is like 5.01 or something, so it's pretty much spot on. But if I start putting different things on, so if I put a CH3, they're low in electronegativity, they will actually share electron density just a little bit. So when it shares it in, it can push it over this way. If you push electron density in, so I'm going to draw it like this, then if you make this electron richer, it's going to make it less acidic. So pK goes up to around 5.6. Okay, so let's replace it instead of CH3. What if I did CF3? Well, F is way over here on my list, so it's highly electronegative, it's going to pull away. So now we have a case where it's going to pull out, which means this is electron poorer. Electron poorer means more acidic. More acidic would mean lower pK. So 3.8. So that's actually a pretty substantial drop. That's not quite in the ballpark of resonance, but still pretty big, over one of a drop. Oh, oops, electron poorer. So we're going to do the same thing comparison, but now instead of using, well, benzoic acid, I'm going to go to, let's see, I have a CH3 next to a carbonyl. I know that group is ACE. So this must be acetic acid. So acetic acid, also known as ethanoic acid. So if we put fluorines in place of hydrogens, hydrogens donate in slightly because they're less electronegative than carbon, which means there's going to be a slight impact here, which means slight impact here. So we have that number. Whereas fluorine's highly electronegative, according to Fonkelbrish. It's going to pull away, and pull away. So it's going to make it more acidic. So that one's going to end up dropping all the way down to about 0.23. Because again, fluorines are significant. One fluorine, or I guess the one fluorine will have an effect. Three is just that much more magnified. And unlike the previous example where it went down by 1.2, those fluorines were far away because they had to go all the way through that benzene ring. Here, because they're so close, the impact is more significant. So just like before, the closer you are, the greater the effect. Okay. So this one is going to be more acidic than this because I replaced H's with Cl, something more electronegative, but not as much as fluorine. So it's got to be less than this number because of the inductive effect, but not to the same magnitude of going all the way down to 0.23. That one ends up being 0.66. Okay, still pulls it down a lot, so electronegativity is definitely going to play a role. Now, if I compare this one to this one, it's still chlorine, it's still 3 chlorines to be exact, but they're further away. So again, forces go down with distance. So as chlorines get pulled further away, you end up having less of an inductive effect. So it still is going to go down from 4.74, but not all the way down here. So we find it's around 2.34. So distance impacts it, and then strength of what's pulling it away or donating in affects it. So just like before, strength of charge affects induction, proximity affects induction. How close it is to the acidic group, proximity affects inductive effect, strength of the withdrawing group affects the inductive effect. So same things we know in physics apply here. What if we only have one chlorine? So this compared to this, 3 chlorines pulls it down a lot. 1 chlorine is only going to pull it down maybe a third compared to 3 H's. So I'm going to take an educated guess that if this difference here is what, around four-ish, 4 divided by 3 chlorine is about 1.33 per chlorine. So if I drop out 1.33, I'm going to say about 3.4. Let's see if it works this way. Absolutely doesn't. So the reason it doesn't, and just want to toss this in your head so you don't think along those lines, it's a natural thought. People ask that question all the time. This is a log scale. So the further you get from 7, the more extreme it's getting. So just to put this in perspective, 0.23 and 0.66 are actually further apart than these two numbers because it's a log scale. The magnitude of an increase is more substantial from here to here than it was from there to there. So just keep in mind, because it's a log scale, you cannot divide and space it out in a linear proportional fashion. Okay, but I should be able to at least make a prediction. So if you ran into this on a test that I wrote, I would go along the lines of, can you give me a number for here? And be wide open to say, if you went as low as 1 and all the way up to around 4, it'd be fine. If it's too close to this one or too close to this one, it's not good. But if it's somewhere between those two values, then you're doing well. 2 chlorines, more than 1, but less than 3. So it should be somewhere in that range. Hopefully this isn't too extreme. So the bigger withdrawing group makes it go down more. Proximity, the further away, it goes down less. And then the number you have. So 1 compared to 2 compared to 3 will have that impact. That's a so-called inductive effect. You got no Funkelbrich. Resonance is most important, inductive is second. So RI. So if I want to go through questions on this, and this is definitely an OChem topic, as a test writer, I have to figure out different ways I can ask the same question, but word it differently to sound like it's a new question. You as a test taker have to try to outthink the test writer. So whether you're in my class or whether you just happen to have found this on the internet and are using this to supplement your class, your professor, or if your professor happens to be me, will be wording these things in different ways. So know how to ask the same question. So if I want to ask the very basic question, which acid is stronger, so many different ways I can do it. Go with pKa, conjugate strength, some of the definitions like Lewis, Bronsted-Lowry, can go in a lot of different ways. So for instance, I could go with the whole conjugate base. So which acid is stronger? Well, which acid has a weaker conjugate base? It's a more convoluted question. It adds a whole extra step that you have to convert from weaker conjugate base to stronger acid. Which acid is a better proton donor? So I've gone with the fact that you have to know a proton donor is a Bronsted-Lowry. You don't have to know that it is Bronsted-Lowry, but you need to know that one of the definitions is proton donor. So which acid is a better proton donor is asking which one is a better or stronger acid or reactive acid. Which acid is a better electron pair acceptor? So again, you have to know that that's the definition of an acid. If you know it's Lewis, great. If you don't, you just know that's an acid definition, then you're set. Which acid gives a higher Ka when reacting with a given base, such as ammonia? Okay, that's a weird question, but it should make sense. The higher the Ka, the stronger the acid. So if it reacts with a base, the more it reacts with the base, the higher the Ka, or K equilibrium, excuse me, which means the more acidic the compound, the more reactive the compound. Which acid has a greater Ka? That's a straight definition, which also means lower pK is the same thing. Which has a conjugate base with a lower Kb. So that's really getting convoluted. It's doing this combined with something like this. The point is, I could keep going with more. Your job, know different ways to answer or ask the same question and then know how to answer all 8 of these questions the exact same way. Which acid is stronger is going to be the question. You can whittle down any question they give to which acid is stronger. Okay. So now to answer that question, which acid is stronger? So if I break it down, and I'm going to show carboxylic acid just for ease and simplicity at first. So here are the factors at play. The very first atom attached is your primary factor. Everything else is secondary. So I need to analyze what's affecting this. So if this is a really electronegative atom, it'll take electrons away, it'll make it more acidic. If it's a really large atom, it's a longer bond. Longer bonds are weaker, break more easily, it'll make it more acidic. If it has a hybridization, that makes it a shorter or longer bond, that's going to affect it as well. So just the S character, the more acidic it gets, that's going to pull the electrons closer to the nucleus and steal it back, leaving an H plus. So more S character will make it more acidic. So there's factors at play, which will include, in this case, atomic size, how big it is, that'll affect the bond, electronegativity, and hybridization. So I'm going to erase my picture so the definition can come in. So bigger atoms form longer bonds, which are weaker bonds. Weaker bonds break more easily. So if I consider, for instance, a thiol versus an alcohol, that's a classic example. So there's my thiol, there's my alcohol. The difference between O and S is below O in the periodic table. So it is larger. So longer, shorter. pK is around 10, pK is around 15. So really it's 10 to 12, 15 to 16. Larger pK, smaller pK goes with the longer bond. So longer bond, weaker or stronger acid, excuse me. Okay, so that fits for that one. Electronegativity. This one also can be true because O is more electronegative than S, but it's backwards. So I need to figure out when it applies. So this one I'm going to do H bonded to fluorine compared to H bonded to O. O is less electronegative. This is more electronegative. I'm just going to put more electroneg. So it's going to pull electrons more, give it off as delta plus. This will pour a little bit less. This has a pK of 3.3. This again is a pK of 15 to 16. That one's more acidic. Okay, so I just came up with contrary rules, but I didn't. When I go down a periodic table, size matters. When I go across a periodic table, electronegativity matters. So it's not only knowing what the impact is, but knowing how the atoms relate. So that's going to be a tricky part. And then finally, hybridization, more S character means more acidic. So that just you flat have to know it. So that's a case where you're going to have different acidity according. So I want to do that example I did, but now with prettier pictures. So down the periodic table, we have element 8, 16, and 34. Oxygen, sulfur, selenium. And I'm going to do that same thing. I'm going to compare the SEH, the SH, and the OH. Their pKs are respectively around 5 to 6, 10 to 12, and 15 to 17. So the higher the pK, the weaker the acid, lower the pK, the stronger the acid. So the acid is getting stronger as you go down because the bond is getting longer and longer. So when I go left to right, I worry about electronegativity. So same example as the previous page, but now with numbers to solidify it. So good thing to remember, if you can draw this kind of like a crossword puzzle and visualize this, electronegativity and size. So if you have a crossword puzzle like that, size for up and down, electronegativity for left and right. So when I'm comparing two elements above and below one another, worry about the size. When comparing side by side, worry about electronegativity. And then finally for hybrid, this we've already done. But now I'll specify this. I said 25 before, it ends up acetylene is 26. Ethene is around 40-ish, and this one's around 49-ish. So SP, SP2, SP3. Okay, those are the primary effects. So if I want to compare H bonded to two different elements, I can do that. The secondary effects, the rest of the molecule. Resonance always wins. Resonance is always your winner. So if resonance predicts something, that's what we go with. So it may completely oppose inductive effect, resonance win, because the actual moving of pi electrons is easier to do than just electronegative pull through mostly the sigma bonds. So we went through all of these before. So hopefully those seem familiar. All of these is in these two. Solvation in sterics. So there's one last thing that comes into play, and that is how crowded the molecules are. So it's something known as steric hindrance. So it's going to pop up. It doesn't come into play that often, but if a molecule is really, really crowded, then it might not be able to react with another molecule, so it may not be as acidic. So if the carbons on it are so bulky and they get in the way, then it reduces how much it can react. Less reactive means weaker acid. Okay, so these same things shown picture-wise. This example here, we have N with two H's and a CH3. So it's one was an amine. Here it's an amide. So it has one withdrawing group by resonance. This has no withdrawing group by resonance. This one has one. Actually, let me choose a different color. One or two. So double withdrawal, single withdrawal, no withdrawal. The more you withdraw, the more you make it relative acidity go up. The other thing, and I apologize, should have just then done this right away, primary effect. Do I consider H's on carbon, or nitrogen? So nitrogen's more electronegative, so this is what I need to compare, the H on an N, the H on an N, H on an N from compound to compound. And then I consider resonance. So this is most acidic, next, and this is the least. Okay, so your pKs bear it out. The inductive effect. So we did this one already, but I'll just reemphasize. If you have 3 fluorines versus 2 chlorines versus no chlorines, then you'll have major inductive effect, significant effect, and no effect. So this one, if you recall, was in the 0.3 range roughly. This one was in the 0.6 so range roughly. So I think 0.26 or something like that, 0.66, something of that nature. And this should be 3.74, 23. Okay, and then solvation in sterics. So how crowded they are. So what happens is this is a just 2 carbon chain, not very crowded. This is a bulky 4 carbon blob. Because this is so bulky, it's hard for this molecule to move around and react. Steric hindrance hinders its reactivity, gets in the way. Less reactive means less strength. Less strength means higher pK. So pK 10.62 as opposed to 11.05. Okay, so primary effects, secondary effects. So it's considered initially the size of the atom, electronegativity atom, and when you're comparing, decide if they go up and down or left or right in a column, or up and down column, left or right in a row, and then hybridization. And once you've done through that, then look at the secondary effects. Resonance is more important than inductive effect. Inductive is more of an impact than sterics and solvation. Solvation, I call it that because sometimes the solvent can cling to it and also make it unreactive. So it's a steric hindrance, but complements of the solvent clinging to it. Okay, so let's try some questions. What is the pK for the side chain of the following amino acid? Cysteine shown, and in case we're going to show it at 7.4 physiological pH. So we have this. So the amino terminal is positively charged, the carboxyl terminal is negatively charged, and apparently the CH2SH is neutral. So what we know is the following. If it is protonated, then the pKa must be greater. So the pH must be less than the pKa. So in this case, 7.4 protonated, so the pH 7.4 and the pKa, pH is less than the pK. So I know the pKa is less than 7.4, but I also need to consider what's going on over here. This is protonated as well, but it's positive, so its pK is around 10. Because still protonated, something for it's less than 10, so I also know that to be true then. So I can use that to figure out approximately what's true, the pK here relative to 7.4 and this one. And so my memorization, I know this is 10. Okay, so if they're both protonated, all I know for sure is this is greater than 7.4. Can't tell for sure. And so it's 8.36. So you wouldn't necessarily know one way or the other. So I would have to make some sort of thought, and that is the inductive effect. The positive charge and the electron withdrawing nature of this being close is going to affect it. This negative is going to push back the other way and maybe not effective, but it is one carbon further away. So if I draw this out, the negative's on the O, which is 1, 2, 3, 4, 5 atoms away, whereas nitrogen's 1, 2, 3, 4 atoms away. So the positive's going to repel it and push the H plus away, make it more acidic, more than this is going to pull away. So it ends up as 8.36. Your ability to predict the exact number, not important, but you should note that it's going to end up being a little less acidic than the amine in this case because of the inductive effect of the NH3. Okay, that was a tough question. Don't fret if you don't get it. Get exposed to hard questions in addition to easy questions. Anyway, we are done with yet another podcast. So hopefully they're going well. And I will see you at the next podcast. Bye.